All right, we're going to look at these integration forms. It's not integrating an inverse trig function. It's these integration forms, the result of which is an inverse trig function. These aren't formulas that you have to memorize, but the more we do them, the more we'll recognize, oh, this is that form, and then we can go, look it up to make sure that we've got it right. The first one, we have the integral of du over the square root of a squared minus u squared is arcsine of u over a, plus a constant, of course. For the arctan function, that's du over u squared plus a squared. Note that there is no radical in that one, and that's 1 over a arctan of u over a. And then the second one is really pretty similar to the arcsine one. There are some important differences, though. U is always a function, and a is always a constant in these formulas, so just compare the order of subtraction. The order of subtraction matters, right? So with the arcsecant form, it's the function first minus the constant. Also, of course, we've got that factor of u outside that makes it stand out a bit. So let's do some practice. Our first one, this is dx over the square root of 4 minus x squared. Well, this fits the arcsine form. This fits the arcsine form where a is equal to 2 and u is equal to x. And if u is x, then du is just plain old dx. So there's no, we don't have to compensate or add any constant factors. This matches up pretty perfectly. And so the result is arcsine of u over a is x over 2, and then plus a constant. In part B, we've got another one here, and notice there's no radicals. So I'm thinking probably this is an arctan form, and I think it fits it pretty well. In the arctan form, a would have to be the square root of 2. These are squares that appear in these formulas. So a is the square root of 2. And if u squared is 9x squared, that means that u has to equal 3x. And so du is 3 dx. This time we do need to add a factor. We need to add a factor of 3. We'll compensate with the 1/3 out here. So now I think we're ready. This is 1/3 times, and then the formula says 1 over a arctan of u over a. So that will be 1 over root 2 arctan 3x over root 2 plus a constant. I'll clean this up a little bit. So we have 1 over 3 root 2 arctan of 3x over root 2. You could leave it like this. Some folks might have an instinct and really kind of maybe want to rationalize the denominator. Feel free to do that. If you do, I think you get root 2 over 6 arctan of, let's see, 3 root 2 x over 2. Either's fine. Alright, so for this next one, we have dx over the square root of e to the 2x minus 1. Well, let's see here. I guess one of the first things that stands out to me is we've got a radical on the bottom and we've got some subtraction. So I'm thinking arcsine or arcsecant. Note that in this case the function comes first. So this might be an arcsecant form. I'm a little concerned at first that we just have a plain dx and I don't seem to have my u yet, but let's see if we can't make this work. If it fits the arcsecant form, right, then a has to be 1, u has to be, let's see, u squared is e to the 2x. E to the 2x is e to the x squared. So in fact, u would have to be e to the x, and that means du is e to the x dx. Now, if du is e to the x dx, that means that dx is du over e to the x. And I'm going to do one more step here. E to the x is equal to u, so dx is equal to du over u. So I'm going to make these substitutions. Dx is du over u, so I've got du over u, and then the square root of u squared minus 1. And this does fit arcsecant, where u is e to the x and a is equal to 1. So we just get, normally I think the arcsecant has a 1 over a factor out in front, but a is equal to 1, so I'm going to leave that off. So this is arcsecant of absolute value of u plus a constant, so that's arcsecant of, and e to the x is our u, right? E to the x is always positive, so I'm going to leave off the absolute values. Alright, we got a couple more to go here. This first one, they give us a hint right off, rewriting the integral as a sum of two quotients. So, you know, that we've used this technique before, but you know, if I'm adding or subtracting in the numerator of a fraction, I can split up the fraction over that addition or subtraction. So they're talking about right here, try just splitting it up over that addition. So that'll be x over the square root of 4 minus x squared dx plus 2 over the square root of 4 minus x squared dx. Alright, now because we've split it up, we can approach each of these integrals like it's its own separate problem. The first one that we look at, we've got 4 minus x squared in the bottom, but up top we have this factor of x, and that's really close to the derivative of 4 minus x squared. So I think for this first one, what we can do is let u equal 4 minus x squared, then du is negative 2x dx. We'll need a factor of negative 2 here, which will compensate for outside. And then we'll rewrite this. Instead of the square root in the bottom, I'm going to write that as a negative 1/2 power u to the negative 1/2 du. So that first one is a power rule integral. Over here, I don't have a factor of x up top, so this is not going to be a power rule. But it does, however, fit the form of arcsine. It fits the form of arcsine where a is equal to 2 and u is equal to x. The only thing we have to do is actually just pull this factor of 2 out of the integral. Now we can integrate both of these. The first one is the power rule, so we have negative 1/2. Then we've got u to the positive 1/2 times 2 plus 2 times, this is arcsine of u over a, so that's x over 2 plus a constant. I'm going to simplify and throw the expression back in with x's for u. So I'm going to cancel these 2's here. So I got negative square root of 4 minus x squared plus 2 arcsine of x over 2 plus a constant. Alright, for this next one, so our last one in this section, the hint they give us, improper rational function, divide first. So looking at this fraction that we have inside inside the integral, I've got a cube on top of a quadratic. It is an improper fraction. You know, anytime we're dividing and the degree of the polynomial up top is greater than or equal to the degree on the bottom, we think of that as an improper function, or an improper fraction rather. And so we're going to just do the division first. So we're going to divide 3x cubed minus 2 we're going to divide that by x squared plus 4. So the first, looking at the first terms, we multiply x squared by 3x to get x cubed, so there's our first term. I'm going to take that 3x and multiply it by the divisor to get 3x cubed plus 12x. Now I have to subtract this whole thing. The 3x cubes cancel. I've got to bring down the 12x. That's a negative 12x. I have to remember I'm subtracting the whole thing. Minus 12x minus 2. And now we're done because the degree of our remainder here is less than the degree of our divisor. So that means that 3x cubed, let's see, let me write this out. That means that 3x cubed minus 2 over x squared plus 4 is equal to 3x, and then plus negative 12x minus 2 over x squared plus 4. All right, so this is our takeaway from this process. Now what we're going to do is split up this integral, right? We're gonna split it up over this addition right here, but also we're going to split up this fraction, right, over that subtraction there. So what we end up with is the integral of 3x dx, and then we have minus the integral of 12x over x squared plus 4 dx, and then minus the integral of 2 over x squared plus 4 dx. Alright, the first integral we know how to do. What I'm going to do is sort of work with each of these and make sure we're at a point where we know how to integrate them all, and then I kind of integrate them all in one go. So I'm going to bring down the integral of 3x dx. The second integral is really close to, you know, what I have up top is very close to just being the derivative of what's on the bottom. So what I'm going to do is peel out a factor of 6 from that 12x, so that what I'm left with in the numerator is 2x. So I got minus 6 times the integral of 2x over x squared plus 4. And now with that integral, if what I have on top is the derivative of what's on the bottom, that'll be a log form. So that's a log rule integral. And then last, I'm going to take this 2 in the last integral here. I'm going to just pull it outside the integral. And now I don't have an x up there, right? So it's not going to be a log rule, but it is an Arctan form. I've got u squared plus a squared, where u is equal to x, right? And then du is dx. So this sort of perfectly fits that Arctan form. Now I'm going to integrate everything. The integral of 3x using the power rule is 3/2 x squared minus 6 times this middle integral. That's a log form, so this is ln of x squared plus 4. Usually we'd say absolute, value of the denominator, but x squared plus 4 is always positive, so I'm going to leave off the absolute values. And then minus 2 times, this is the arctan form, so it's the arctan form where a is equal to 2 and u is equal to x. So that would be 1 over 2 arctan of x over 2 plus a constant. And now I'm just cleaning it up ever so slightly. I'm going to cancel these 2's here. That's basically all there is to do. Okay, I may have improperly earlier said that this is the last one in this section, which is not true, because I almost was ready to stop before we got to what is probably the most fun part. Anybody who's taken a course with me before knows how much I love completing the square, and any opportunity to complete the square is a gift, and we should appreciate that, or at least I do appreciate that. So completing the square, maybe it's not so surprising that completing the square, it shows up in this section. And I'm going to just scroll back to these formulas. In these formulas, they're all about, we have to see these perfect squares in them. Now, sometimes we might be really close to having a perfect square. And by completing the square, we can see, the form kind of reveal itself to us. We could see that maybe something that doesn't initially look like an arctan form maybe is an arctan form. This example of part A, that doesn't look like an arctan form at all. I've got this quadratic in the bottom of a fraction. But let's see what happens when we complete the square. When we complete the square, so my quadratic is x squared minus 4x plus 7, and what I'm going to do to start is I'm going to write the first 2 terms. I'm going to leave some space for completing the square, and then I'm going to write the last term after giving myself a little bit of space, because what I'm going to do right here in that space is complete the square. So we take a look at that coefficient on x. We're going to cut it in half, and then we're going to square it. So we're going to add the square of negative 2. And now if I were solving an equation, what I would do now is just add the same thing to the other side. But we don't have an equation, we just have an expression. So what I'm going to do is subtract this. Right, so I'm just adding and subtracting the same thing. Now this right here is a perfect square. It's the square of x minus 2, right? We're just going to take this right here and that there, and there's our perfect square. Now we just have a little bit of arithmetic to do at the end. 7 minus 4 is 3. So now we have x minus 2 squared plus 3. I'm going to rewrite this integral now. I've got dx over x minus 2 squared plus 3. This now fits an arctan form. This is the arctan form where u is equal to x minus 2, du is just dx, and a is the square root of 3. And so integrating this, there's no constant factors we need to throw in to correct for anything. It fits really well. So it's going to be 1 over root 3 arctan of x minus 2 over root 3 plus a constant. Oh, we're going to do one more. This time we've got dx over 2x squared minus 8x plus 10, another quadratic. Now, this is going to work out kind of similarly. I chose this one right here because the coefficient on x squared isn't just 1. When the coefficient on x squared is anything other than 1, completing the square requires an extra step. So I just wanted to do this example to show that. And what I'm going to do first is I'm going to factor out a 2 just from the first two terms. Just from the first two terms. All right, so I'm going to have 2 times x squared minus 8x. I'm going to leave space, close those parentheses, and then there's my plus 10. What I have written out right now in black is equal to the denominator of that fraction. I'm going to complete the square of, oh, you know what? Hold on one second. I made a little mistake. What I have written down is almost equal. I factored out a 2, but I forgot to factor it out of this middle term. So that's actually 4x. There we go. Now what I have written down in black here is equal to that denominator. So I'm going to complete the square on the stuff in the parentheses. I'm going to add the square of negative 2. And of course I don't have an equation, I have an expression, and I need to subtract that too. But what we have to realize is that I did not just add the square of negative 2 to this expression. That is sitting inside parentheses being multiplied by 2. So when I subtract it off, I have to bring that factor of 2 with me. So now this looks like 2 parentheses, and then x minus 2 squared. And doing some arithmetic here, that's 4 times 2 is 8, so that'll be plus 2. And so now I'm going to replace the denominator with that expression. Now that's not quite the arctan form, but it's really close. I'm going to factor out a 2 from the bottom. And then I'm going to take out this 2. Of course, that 2 being in the bottom means I'm really taking out a factor of 1/2. Now this is an arctan. It's really similar to the last one, actually. This is an arctan form where u is x minus 2, du is dx. This time a is equal to 1. So this becomes 1/2 times arctan of x minus 2 plus a constant. Now these were both, you know, the examples on this page where we're completing the square were both ones where we ended up with arctan, but this is something that also can happen with arcsine or arcsecant. You know, if you see the radical, you can complete the square on an expression that appears in a radical as well, just as you can complete the square on an expression outside the radical like we did with these.